Hi, my name is Amy, and this is my research titled Increasing the Electrostatic Force Between Spacecraft Using a Pulsed Electron Beam. This research is a continuation of work related to the electrostatic tractor, which is a concept for contactless debris removal in GEO. The concept states that a servicer spacecraft aims an electron beam at a target debris object. The impact of the electron current on the target causes it to charge negatively, while electron emissions charge the servicer positively. An attractive force that allows the servicer to reorbit the debris to a graveyard orbit is the result. We focus on GEO for a few reasons. First, the spatial density for objects in GEO is relatively high, and 95% of all insured satellites reside there. Despite that, around 50% of satellites are non-compliant with IADC regulations at the end of their life, falling short of the suggested graveyard orbit or being completely abandoned. In addition, contactless debris removal is essential for GEO debris because defunct spacecraft have been observed to tumble at rates on the order of tens of degrees per second. Finally, the typically low density of the plasma environment prevents Debye shielding that would prevent the electrostatic force to be felt over suitable distances. Previous research on the electrostatic tractor has shown the Coulomb force between the target and servicer is on the order of millinewtons or less, depending on e-beam parameters and separation distance. This invokes the question, how can we increase this force to make reorbiting large debris faster and more efficient? The answer to that lies in the fact that the previous research used a continuous electron beam. In this study, we explore how a pulsed electron beam can enhance the electrostatic force between the spacecraft. In order for that to make any sense, we need to start off with some backgrounds. First, let's take a look at the forces that are acting on our servicer spacecraft, highlighted in green in the figure to show that it's charged positively. The servicer spacecraft is equipped with thrusters, so there's a force of thrust pointing away from the target. Pointing toward the target, there's an electrostatic force that I've mentioned several times now. As you can see, the electrostatic force is inversely proportional to the square of the separation distance. Thus, if the force of thrust is significantly larger than the electrostatic force, then the electrostatic force will go to zero and the servicer will run away from the target. Previous research found that the force of thrust required to maintain a fixed separation previous research found the force of thrust required to maintain a fixed separation distance for reorbiting debris, shown here as the first equation. Finally, to quantify the force into tangible measurements, we'll calculate the reorbit time dependent on a delta V of around 11 meters per second. In order to increase the burn time by decreasing the force of thrust, we must work to increase the electrostatic force. Next, I'll explain how the pulsed beam concept can actually increase the force compared to the continuous beam. The power for a continuous e-beam is calculated using the simple equation P equals IV, where I is the e-beam current and V is the e-beam voltage. For a pulsed beam, that equation becomes P equals duty cycle times the pulsed current times the pulsed voltage. Because P is fixed for a given electron gun, IP and VP must be scaled accordingly by dividing by the square root of the duty cycle. There's also a tuning parameter, gamma, that can be that can be included in this equation if the current and voltage are to be scaled differently. But in this study, we'll just be using gamma equals 1 because this has been shown to be near optimal in previous papers on this topic. Finally, these studies will be conducted in a simulated bi-Maxwellian plasma environment. The flux distribution equations are shown here. GEO is known to be bi-Maxwellian, especially during active periods such as geomagnetic storms and substorms. During quiet periods, cold plasmasphere particles may expand past GEO. The effect of the changing environment will be explored in this study. First, we'll explore how duty cycle affects the maximum electrostatic force. The figure shows the charging and force responses of the pulsed beam with duty cycles from 10% to 90%. The beam current is 520 microamps, and the plasma parameters corresponds to active conditions with a Kp index of 6 and a local time of 4. What we find is that the average force across a pulsing cycle increases as the duty cycle decreases. Then we ask, is there an optimal duty cycle such that the force is maximized? The reason this might be the case is because at some point the beam will not be turned on long enough to charge the spacecraft sufficiently. So even though the current and voltage are increased significantly, the target just doesn't charge fast enough. And the answer to that question is yes. The force for these beam and environment parameters has an optimal duty cycle of around 4.5%. We find that by optimizing the duty cycle, we can decrease the reorbit time from 93 days for a continuous beam to only 5 days for the pulsed beam. This is all very promising, but I'm leaving out something very significant, the photoelectron current. The previous results are for spacecraft in eclipse, so the next section will discuss how the photoelectron current impacts the electrostatic force enhancement using a pulsed beam. You might be asking yourself, why is the photoelectron current so significant? Well, in GEO, spacecraft are actually very rarely in eclipse. For example, the ATS-5 spacecraft only entered eclipse for 90 minutes each night for a period of 3 to 4 weeks on either side of an equinox. In addition, the photoelectron current tends to dominate all other currents in GEO. Thus, neglecting its presence doesn't provide a full picture of spacecraft charging. Back to square one, with duty cycles ranging from 10% to 90%, we can see that this time the spacecraft doesn't even charge at higher duty cycles. At lower duty cycles, the current and voltage of the electron beam are enhanced enough that the spacecraft can overcome the dominating photoelectron current. This figure shows how the percent of the projected area exposed to sunlight impacts the average electrostatic force on the spacecraft using a pulsed beam at its optimal duty cycle. We can see that the force decreases as the percent exposed to sunlight increases, which is what we expected. But regardless, the average force produced by the optimal pulsed beam is nearly 6 times larger in total sunlight than for the continuous beam in an eclipse. Now we'll briefly explore how the changing GEO environment impacts charging using the pulsed beam. Figure A shows the maximum average force as a function of the Kp index, which is a measure of geomagnetic activity. Figure B shows the maximum average force as a function of the local time, which ranges from 1 to 24. Geomagnetic substorms occur between local midnight, which is 0 or 24, and local dawn, which is around 6. During active periods, hot plasma is injected into GEO, which assists with spacecraft charging. During quiet periods, cold plasmasphere particles expand into GEO, which hinders spacecraft charging. We can clearly see that at low Kp indexes and in the local afternoon, the electrostatic force is minimal, even using the optimal pulsed beam. Thus, the presence of cold plasmasphere particles during quiet periods prevents significant forces. To overcome the plasmasphere particles during quiet times, we explore how the beam power impacts the peak force. First, we need to discuss the impacts that e-beam voltages and currents have individually on the spacecraft charging. The e-beam voltage governs the maximum potential that the spacecraft can charge to. For example, if we use our 40 kilovolt electron beam, then the spacecraft can charge to a maximum of 40 kilovolts. The e-beam current governs how quickly the spacecraft charges. For example, if we use a 520 microamp e-beam, the spacecraft will charge relatively slow. That is compared to a 5 milliamp e-beam. With that information, we know that the maximum potential is 40 volts divided by the square root of the duty cycle, which ends up being around negative 180 kilovolts. Going back to the figure from earlier with the optimal pulsed beam and eclipse, we can see that it gets close. While it gets close, the target does not quite charge quickly enough to reach the maximum potential. Thus, we should increase the current to help the spacecraft charge more quickly and reach higher potentials. This figure illustrates that increasing the current actually does make a significant difference in quiet periods and allows us to overcome environmental limitations. However, limitations related to the electron gun itself still exist if this were to be physically applied. Most importantly, to reach such high potentials, the e-beam would have to have voltages well over 100 kilovolts. In space applications, electron guns do not often exceed 20 kilovolts. The most powerful e-beam for space applications that I am aware of is one being developed by Think Orbital, which will be 6 kilowatts and 20 kilovolts. Another commercially available electron gun, although not intended for space, is this Kimball physics model, which has a maximum operating voltage of 100 kilovolts. To conclude, the pulsed beam is a promising solution for efficiently reorbiting geospace debris. We found that it performs significantly better than the continuous beam in all environments. However, the electron guns currently available limit the pulsed beam as a viable option for debris removal. There are also hazards relating to field emission from such high potentials on spacecraft that are being explored in future research. Thank you for watching my presentation.